semesters, when I'm teaching this class, there are no comets at all. And now there are several. I know. You're like, really? So these are some pictures of some comets. The next slide, actually, I inserted a few pictures I took of a comet. So comets can make about 100 passes. Comets are named by the person who found them. And I didn't realize this until not that long ago. But if you see a lot of P names, there's a lot of P names. That actually is a silly kind of computer that basically finds comets. But if you have kind of like the pretty name, like the Halley comet, Halley Bopp, okay, Hale-Bopp, Halley, two different ones. All right. So these are the ones I took of a comet that I guess his last name was, maybe it was Love and Joy. I'm not sure, but Comet Lovejoy a few years ago. It is pretty. Yeah.
How did you do
That was taken through the telescope. Yep. Yep. So comets, oh my gosh. This right here, kind of from left to right, this figure right here shows, what does it show? Oh yeah. So the thing in the middle that has the kind of yellow and red squiggles coming out of it, that's the sun. And what that's trying to show you, and we were talking about this before class, is the, okay, that's solar wind that blew away Mars' atmosphere. Okay, so that same solar wind actually blows the comet as it's fizzing. So if a comet comes in, this is kind of showing you, I can see these arrows, showing the comet coming in. You see it starts to kind of fizz right there. Okay, as it gets closer to the sun, it's fizzing more. But can you see where the tail is blowing away from the sun? Okay, blowing away from the sun, away from the sun. Now, as the comet comes out this way, can you see where the tail is actually kind of in front of the comet? Why? Because the sun is over here, blowing the tail. Okay, so the tail is always blowing away from the sun, even if that means the tail is blowing in front of it as it moves. Isn't that funny?
Yeah.
I think so too. And they talk about two different parts of a tail. So you see the straight tail, that's the plasma tail, and this curved tail is the dust tail. So they're kind of formed by two different things that are fizzing, basically. So we have the plasma and the dust. Now, can you see two tails on a comet? Well, it depends kind of how it's going down. Sometimes you only see one tail. Sometimes all you see, that green one I took, all you see, this is called the coma. So we have the coma, okay, the circle fizzy stuff. Okay, then we have possibility of two different tails. Like if I go back to this figure, okay, can you see the two tails here? I'm thinking the blue is straight and the pink kind of looks curved to me. Okay, this one I don't see two tails, but dang, I see a coma. So coma, okay, tail. All right. What else do we have? Oh, and then the thing that's still kind of fizzing is called the nucleus. So the chunky thing that's still kind of whole is called the nucleus.
So is like the gravity of the chunky thing pulling the coma in around it? Is that why it sticks on it?
Is the gravity of the chunky thing?
Why does that coma stick
I know.
on it?
I see what you're saying. Why does the coma, why doesn't it become, just blow away?
Yeah.
I kind of maybe think it just keeps being replenished.
Oh.
Like,
it keeps
yeah.
fizzing nonstop.
Yeah, it keeps fizzing. It's coming from the nucleus, and so we kind of have a little bit of fluff. And I don't think it's a gravity thing. I do want to take a minute. What does ESA stands for? It's the analog to NASA. Of course, that's NASA. So it's ESA stands for our allies in space.
Is it European?
It is, the European Space Agency. And I really think that, I don't know when it'll happen, 100 years from now, 200 years from now, if humanity's still here. I really think that we're going to be one global sort of effort in all sorts of things, including space travel, space knowledge. So, Rosetta, oh my gosh, that was definitely a time for champagne. I think we might have even got champagne out. I don't know. I don't drink much, but the Rosetta mission basically caught up with a comet And the Rosetta spacecraft also had a little lander on it called Philae, which means, I think, just like love or something. And so it caught up to the comet, and it got some great pictures of the comet. Okay, I think this was a comet that wasn't fizzing, so it would have been away from the sun. Like, this is so amazing. It orbited the comet, and then it took its little Philae lander and landed on the comet as they're all going into space. Is that not cool or what? So, yay, European Space Agency. So that's been a while. I don't know how many years ago, but just here in March, see if this will come up here. They're real excited, and I don't blame them. Okay. The lander, I think this would be the lander, actually got, this is on a comet, got this picture of like a little cave-in, like a little landslide. Is that not cool or what? That's like a little tiny thing on there. I don't know if you read some of the captions, but the orbiter, so that's from Philae, right? So the orbiter, which is Rosetta, actually is going to do one more kamikaze mission, I think, and kind of plop into the comet. So it's not quite done yet. I just think that's so cool. Okay. What else we got? Comets close up. So that's kind of a comet fizzing, breaking up into little pieces. I think the video we watched maybe talked about this. Again, it has to do with mankind visiting a comet, and they actually, remember they talked about detonating something on the comet? And so this is kind of showing, now why would you want to detonate a comet? If it's coming at you. Like the sci-fi movies, you know? And I've heard scientists say, you know what, if you detonate it, then basically you have a bunch of little things coming at you instead of one big thing, so I don't know. Okay, so, I mean, we've definitely made progress. So one of the things that I'm hoping you take away from this class, and the movie we watched didn't talk about it much, but are meteor showers. So if I go over here, and I kind of got it wrong, I think, but I'll try to get it right this time. What's this?
Earth.
That's the Earth. Very good. And this is the Earth's atmosphere. Very good. And then out here we have a chunk, and it could be an asteroid. If I start with asteroid, I'll get it right. It could be an asteroid, or if it's a little smaller, it will be a meteoroid. Meteoroid. Okay, they're both rocky, don't necessarily have an icy component to them, like a comet. Rocky, space rock. Okay, now as it streaks through the Earth's atmosphere, what do we call it?
Meteor.
A meteor. Meteor. That's the short event. That's the light part. That's the streak part. Oh, I know what we call it. We call it a falling, we call it a falling star. Okay. A meteor is your falling star. Ooh, that one's bright. Okay, meteor is your falling star. Basically, it's a space rock that's burning up in Earth's atmosphere. Meteor is short. Okay, so a meteor shower is where you have a lot of falling stars. Yes?
So the homework questionnaire, it asked about the comets and then the, but it was asking about the relevance for the Oort cloud and the asteroid belt and
Okay.
why they were different or whatever, so
Okay.
Jimmy called my book.
From what you're describing, to me, it just kind of sounds like proximity to the sun. So kind of we have this, asteroids don't have ices because they were too close to the sun. And yeah, and then comets are farther from the sun, and they have it's cool enough to go ahead and get those ices to form.
Okay, that was much more simpler.
Yeah, from what that sounds like. Okay, so like this slide says, now, depending upon how patient you are and how dark your skies are, you can actually see a streak once every 10 minutes, okay? Now, in order to see those, it kind of depends on how good your peripheral vision is a little bit and how dark your skies are, okay? So, once every 10 minutes. Okay, now, a meteor shower happens when the Earth is passing through snow. No. Meteor shower happens when the Earth is passing through debris that was typically left by a comet. Remember we said comets are going to fizz? Okay, so the cool thing is as they fizz, they kind of leave a debris trail. The comets leave a debris trail. They're long gone. Okay, so let's go ahead and we'll make this the sun. Okay, and let's just say a long time ago, a comet came and it came, a lot of times comets come in weird directions. It kind of came down and around, okay, and went that way, and it left a debris trail right here. Right, how do I want to say it? Kind of this way, I guess. Okay, so I am the Earth, okay, and I am orbiting the sun, and I hit this debris field, okay, and then what's going to happen is I'm just going to do my business, and it's really no big deal, nothing bad necessarily. But for that particular time, when I am here, passing through the debris field that the comet left, I'm going to have an extra amount of streaks, an extra amount of stuff falling through my atmosphere. That's a meteor shower. Okay, and they kind of liken it. Look, that looks mesmerizing. If you're like me, if you've driven in the snow, I hate it when the snow is like coming right at you. It's nighttime, and I hate that sensation.
Headlights.
Yes, I do not like that feeling. But that's kind of like the snow would be the debris from the comet, and it's just kind of, okay, but then you pass out of it, okay? So here's the deal, is we talked about, okay, this would be our, this would be our, and we have a tilt like this was our winter solstice, okay? This is our spring equinox, this is our summer solstice, okay? So can you see where that field doesn't move? So it's the same time each year that we pass through this field. So meteor showers happen routinely the same time of the year because that debris field did not move. It totally did not move. The Earth's orbiting the sun, but that little crumblies we're going to run into is in the same place each year. So meteor showers actually happen on a regular basis. And here is kind of when they happen. Okay, this is when they happen, approximate dates. Now, what do these look like? What do these look like? So let's see. They look like constellations, yeah. So what we do basically is we are going to see the streaks coming from kind of a specific part of the sky. And that specific part of the sky gives the name of that meteor shower. So let's see if we find one. Oh, of course, Orion, you recognize Orion, constellation Orion in Orionids. That's a meteor shower that happens in October, and where we're going to see the streaks are in the constellation Orion. Okay, they're the Orionids. We haven't talked, I don't think, about the constellation Lyra. It means lyre, like stringed instrument. Okay, so April 22nd, we have the Lyrid meteor shower coming up. So meteor showers happen because the Earth is passing through comet debris. I guarantee you'll be on your test in some way or another, because, okay. So I went ahead and, to me, if I'm going to get all excited about a meteor shower, a lot of things in astronomy, if you're kind of wanting to kind of get into it, is you need to do a little bit of homework. So here's actually the meteor showers calendar for this year. Now, doing your homework means, for instance, this is the quaternids, and I don't know the constellation very good for quaternids. But this is an important number, ZHR. That means how many is going to fall per hour. 120 per hour, that's a lot. Okay, instead of like 6 per hour, because every 10 minutes, right? 120. Now, if we kind of jack up to the Lyrids, okay, notice how many is going to fall per hour for the Lyrids? 18, yeah. This is the 0 or zenith hour rate. So 18. Yeah, I don't know, I might not stay up too late to see that. The other thing is, why do you think we care about the moon, the phase of the moon? To see those little wispy streaks.
Because if it's really bright, you won't be able to see them.
Yep, because if the moon's really bright, it's not a good time to go watch a meteor shower. Now, you might have heard, there are a few famous ones. Oh my goodness, that's making me dizzy. There are a few famous ones. They happen in August and December. So the Perseids are kind of like the quaternids. 100, that's a lot, Perseids. But what's wrong with this year?
Too bright a moon.
Too bright a moon, yep. The other cool one now, Orionids, that you might have a fighting chance. You kind of see, and sometimes meteor showers happen over like 3 days, sometimes they're like 2 hours, like their peak is kind of different. So the Orionids, that's looking pretty good for this fall. The other one is in December. Ooh, the Geminids. So what constellation would the Geminids come out of, appear to come out of? Gemini, the twins, yeah, the Geminids come out of the constellation Gemini. Yep. And you're back to 120, that's a lot. I've gone out to the observatory, sometimes we have an observing party. Now, if you're gonna do a meteor shower, you don't use a telescope, you just use, because you want as wide of a vision as possible. And I even have a friend out there, we have a friend that actually will bring a clicker and he'll see how many he has to click them. Yeah. So I think that's funny. So there's your meteor showers.
The ZHR is the light value?
The ZHR is the hourly rate. I know HR stands for hourly rate, so it's the number of streaks per hour. So, you know, you want to kind of, and most meteor showers, if I was going to enjoy a meteor shower, I would do my homework the night before. And they'll tell you usually that you want to, or the week before, that you want to see them between like 10 and dawn, 10 p.m. and dawn. I mean, they're kind of sometimes it's like a 2 a.m. thing. And I've kind of set my camera up before, and I'm still kind of, it's a work in progress, just to kind of.
Do planes need to worry about these?
That's a good question. You would think they would be kind of, yeah, that's a good question. But we said, like, the Earth picks up how many tons of just little stuff, you know, a day. So, I don't know. All right, Kuiper Belt. We okay with Kuiper Belt and Oort cloud? Okay, Kuiper Belt's out there in the plane of the ecliptic, basically, and then the Oort cloud is even farther. Okay, and they have the icy bodies. The reason they have the icy bodies is because they're farther from the sun, and ice can go ahead and. So here we have Pluto, and actually next to Pluto, I think, no, not all of them, but a lot of these are actually other Kuiper Belt objects. Sometimes they'll call them Kuiper, K, Belt, B, objects, O. So KBO is Kuiper Belt objects. So Eris was the guy who actually started the demotion of Pluto. So I don't know. The article I read about bringing Pluto back in from a dwarf planet to a real planet is Pluto comes in and then 99 other objects come in, including like the Galilean moons that orbit Jupiter. Why would you make those planets? Like, dude, that just does not make sense. But there's a lot of things that don't make sense to me. So, we'll see. Okay. I think the video talked about this. The video talked about Jupiter. Actually, a comet fell into Jupiter's atmosphere, and it was kind of neat. I think the comet had one pass, and then it was going to have another pass, and they knew the timing and everything, so everybody was looking to see how the comet fragments interacted with Jupiter's atmosphere. Comet Shoemaker-Levy 9, so guess who found it? Shoemaker and Levy. Mr. and Mr., I think. Well. The video also talked about this. Well, actually, there's a few things on this. But kind of down here, clear over to the right, you see of course, you recognize Mexico. And this is an impactor coming in about 65 million years ago, which coincided with the dinosaurs failing. And I hadn't caught it before, but the video talked about actually, you know, that particular event stimulated, stimulated the evolution of other, like marine organisms, that maybe wouldn't have otherwise been stimulated. This right here, I think I don't know if the video talked about it, but there's a really cool story about kind of the layering of rocks. And if you go back to the layer about 65 million years ago, you find, I think this is where the slide says it, the element iridium.
Yep.
And that actually is kind of unique to space rocks. So you're like, dude, Earth, how come you got like a whole kind of fine mist of iridium all about 65 million years ago? And it's actually kind of more evidence that a space rock hit the Earth and kind of vaporized, you know.
Were there polar ice caps then?
65 million years ago? Were they affected?
I mean, were they there?
I don't know. I don't know.
Does the ice go back that far?
I know, you know, from what little I can remember, the ice sheets actually have advanced and retreated over the, you know, hundreds of thousands of years. So 65 million years ago, I'm not sure.
Pretty sure they were.
So what's that?
Pretty sure they were, but I can't say for certain.
I don't know what phase they were in.
They were in all of them.
So will we be struck again? Okay, NEO stands for Near Earth Objects. And the video said yes. When? I don't know. Okay. This actually just kind of says that, let's see, typical time between impacts. And this actually is how big the impactor is along the x-axis. So small impactors like 1 meter, you know, 1 meter, that still seems pretty big. And large impactors, how often does it happen? You know, hundreds of millions of years, you know, once in Earth's history. So. Now, I'm going to take you out to this website. Of course, NASA stands for our space agency. NEO stands for Near Earth Objects. And did you catch on the video that NASA, as part of its, what do you call it, mission, actually has to track near Earth objects? Yes. And this site is all about near Earth objects. I'm going to take you to let's see, where I'm going to take you. Where it says close approaches. Can you see it up there? If you click on close approaches, this is what can keep you up at night.
Oh my.
Yeah, I know. Close approaches, of course we are, what's today, the 24th?
Yeah.
Okay, good. Okay, so these are the close approaches. LD stands for lunar distance, okay? So if you get, you know, 1.7 lunar distances, like Earth and the Moon times about 2, that's how close it was. Yeah. Down here, upcoming close approaches, okay, like this. So these are asteroids, could be comets, but that. What else do we have? Oh yeah, this seems like actually this seems like a long time ago, but it was only, I guess, 3-4 years ago. This is not the sun. This actually is a meteor streaking in through a space rock streaking into through Earth's atmosphere. So Russia got kind of a jolt. Okay.
Oh, I remember seeing that in the news.
And the explosion in the atmosphere actually caused windows and everything to break, you know, in the vicinity, or not even necessarily in the vicinity. So.
10,000 tons?
That's crazy. And then one last slide, and we'll take a quick look at Chapter 9. The video talked about this too, where you can kind of see all sorts of crumblies here, right? The crumblies would be your asteroids, maybe comets. And as it turns out, our Jovian planets have kind of done a good job of blocking it sometimes, in some cases, incoming stuff. But also, didn't the video say, or I think you can read it on this slide too, that Jupiter can actually kind of, its gravity, give a push for an asteroid in the asteroid belt to come out of its kind of neat little pattern. So Jupiter can do that, and also then out here, Neptune can give like a nudge to a comet and kind of change it, instead of kind of just orbiting the sun, kind of bring it inward. So anyway, there's always good and bad. What do you gotta do? Okay. So let's take a look at, and then we'll see what we want to do Monday. Let's look at 10. Yeah, there's only 5 slides, 6 slides. Okay, like really? Okay. So you're like, what the heck? We're definitely switching gears here. Now, what do we say about stars? Do most of them have planets? Yeah. And you can imagine, I mean, if you look at even what appears, well, I heard you guys say this. You're like, okay, Sirius, it's like really bright. Well, now, is it really bright because it's pumping out the energy, or is Sirius really bright because it's close to us? Well, you know, we have to take that into consideration. But Sirius, it's hard to kind of look at the region around Sirius to see if it has any planets. This is a common deal. This thing in the middle is the star. And so what they do basically is they block out the star. You're like, dude, I don't want to see the star. And they look for stuff around it. Now this actually would be a direct detection of planets. There's direct and indirect. So to see the planets directly is a crazy sort of thing.
Is there a way to tell if it's in the Goldilocks zone, like from
Yes,
that view?
yeah, she's asking about the Goldilocks, I don't know, I would think so.
Yeah.
She's asking about the Goldilocks zone. If you know information about the star, which you do, then you know information about its heat output and you know what zone a planet would need to be in to be habitable. Now, the zones for being habitable, as far as I can tell, is basically liquid water. So you basically have to be able to have liquid water. So
Are we looking at on top of its plane of ecliptic?
that's what it looks like to me. It looks like we're looking at what we call face on. Yep. And this down here, okay, this actually is a player in looking for extrasolar planets. This is a telescope kind of like the Hubble Space Telescope. Everybody knows the HST, the Hubble Space Telescope, okay? Maybe people don't know the Keck Telescope, which actually is not in operation now, but it has all sorts of data we're still sifting through, or they're still sifting through. So the Keck Telescope, I don't know if it was this type of orbit or this type of orbit, but it orbited the Earth, and it looked out there, and the only thing it looked for or studied stars looking for planets. Like, what a lonely thing. No, I don't know. I'm pretty sure, like, it was February, maybe, that the big Stiel came up with all these planets orbiting this star, and I have a link to it. And that's old Keck data, old Keck telescope data. Okay, so yeah, that would be direct detection. And that was like a face-on, kind of looking at the planet into the plane of their ecliptic. So we know, because of what the internet says. No, we know because of what science has told us that most stars actually have planets orbiting them. But as late as 1992, which for you whippersnappers was just the other day, they weren't sure whether other stars had planets or not. So the term extrasolar planets, okay, that might be a good word to throw in your test. What is an extrasolar planet?
A planet that's outside of our solar system.
Yes, a planet that's outside of our solar system, a planet that's orbiting another star. Now, you might wonder, and this is so crazy, I think one of the videos we want to talk about, they're actually wandering planets that don't have a star, don't have a star. Oh, isn't that weird?
So maybe they got flung from.
Yeah, I think they maybe got flung or something. They're homeless planets. Okay, and this number is increasing, the number of extrasolar planets that we know about. So like I said, it's a challenge. It's a challenge for a number of reasons. One is because their star is so far away, and one is because the planets are pretty small, and the other is because their star is so darn bright. So you're like, you kind of have the chips going against you. So most extrasolar planets are detected not directly but indirectly. Okay? I'm going to kind of try to tell you a little bit about what indirectly means. You're like, well, if I can't see it, I don't believe in it. Well, can you see the wind? You know, do you believe in the wind? Yeah? Okay. And actually, indirect detection, there's 2 ways. I'll run these past you. I think you guys have homework questions over these. The 2 indirect ways. One is to see the star, now not the planet, but you see the star moving a little bit. One of the things, let's see, do I have it here? Actually, our star moves a little bit because of the presence of Jupiter. This is the sun, and this is Jupiter, and Jupiter's so big that it makes actually the sun move just a little bit. I'm going to try to go like this. Okay, it makes the sun move just a little bit. And if you can see that, then you know that it has a planet orbiting it. So, oh, are you serious? Yes, like it's a gravity. That's a gravity thing. So how do you see this wobble? Well, there's two ways to see this wobble. There's actually, if I was wobbling like that, you could see my wobble. Okay, but if you're like this, you can't see my wobble unless you do the Doppler. Remember we talked about the red, sorry, this would be blue. We talked about the blue shift and the red shift. Okay, if there's this, you're going, oh my gosh, that would be so crazy. You see blue, red, blue, red. It's wobbling. Why? Because it's got a planet orbiting it. Is that not cool? Okay, so that's that. And then the other one is kind of fun. They both seem so tedious to me. I just give them kudos, kudos, kudos. And again, the Kepler's given all sorts of data so scientists can do this. The other one, and this one kind of makes sense to me, and it only works if, okay, I think an edge-on view. So if you guys are Earth and this is the sun, okay, what happens is the sun sends a lot of light, okay? Now, if this is the planet, okay, it's sending some light, not really sending light, it would be reflecting from the star. But my point is here, what if I put the planet here? It blocks out a little bit of the star's light. How much? Not much. Okay, so we call this transiting. Okay, if this is the star and this is the planet, as the planet moves in front of the star, it blocks a little bit of light. So this actually is a light meter. This right here is where there's no planet in front of the star. This dip is because the planet moves in front of the star, and over here the planet has gotten to the other side of the star and you can see all the starlight again. Very, very subtle. Like, really?
Gosh, well, how can you detect that?
How can you detect that?
That's crazy.
It is crazy. It's people that are determined to. Astronomy is like taking every little bit of information that anything in the cosmos wants to send you and making the most of it. And there you go. It's amazing. So that hubbub about those, I looked at it this morning, there's 7 planets orbiting, terrestrial planets orbiting this star that was kind of came out the other day, and 3 of them are in the Goldilocks zone. And how do we know that? You know, just exactly what we're talking about here. All right. So extrasolar planets, what do they look like? Okay. Well, over here, what can we know about an extrasolar planet? The period, what do you think the period is?
How long it takes for them to orbit.
Yep, how long it takes for them to orbit their star, exactly. That's the period. Their distance from their star, what's eccentricity?
The ellipse.
Yeah, how elliptical it is, or how circular, or how kind of oval. We can know that. We can get a sense of the mass, the size of the planet, the density of the planet, because if we're going to visit, we need to know if it's Jovian or terrestrial, right? The atmosphere of the planet. Are you serious?
No way. So they could tell the atmosphere of those planets.
Depending, yes. And actually, I think the article I have coming up says they know, they have a sense, well, not just a sense, they have evidence of what the atmosphere around those planets are. Like, oh! So Kepler, of course, is that spacecraft, like the Hubble, telescope, like the Hubble Space Telescope, the Kepler telescope. And I'm not sure how they named the planets that it found, but let's see. Do you recognize these as kind of light curves over here? Okay. So, go Kepler. Oh my gosh. Hats off to you. So, extrasolar planets. What do they look like? Well, this says, and we kind of talked about the Goldilocks zone. If a planet gets too close to its sun, bad. Too far away from its sun, bad too. So, if it's kind of like very elliptical, if the orbit is highly elliptical, there's issues, okay? Our orbit's a little bit elliptical, so we kind of have what we call perihelion and aphelion, but, yeah. Let's see. What else did I say? And this says the whole wobble thing, indirectly determining or indirectly knowing there's a planet there. If the planet takes a long time to orbit its star, then it's gonna take forever to see the wobble. So patience, I don't know, you know. So there you go, there's a number, 70%. So we've been saying most, I'll say 70% is most. So about 70% of the stars that we've been looking at, we see actually have at least one planet. The small extrasolar planets are more common. That's what this is showing you. So the thing down here are how big the Earth is. So from 0.8 of the Earth to 1.25 of the size of the Earth, you're looking at about, I don't know, 16% are all kind of that size. About 20% are up to 2 times the size of the Earth, mass of the Earth. 2 to 4 times the mass of the Earth, you get another 20%. So these kind of gas giants out here are a lesser percentage. The densities range from iron to styrofoam. So this last slide just kind of, it's a cluster diagram. Each dot represents a different extrasolar planet. Let's see. This little blue box here, we talked about kind of similar Earth planets. Not very many dots in there. Okay, right here. This I'll just kind of leave it to you to look at. But the big excitement actually was, oops, this one. NASA discovers 3 extrasolar planets with the possibility of organic life. Really? Yeah, and that was just dated February. So it's the TRAPPIST system of planets. There's an artist drawing. Those are not photographs, people. Okay. But if you read it, it will talk about, it mentions Kepler. So, and I think it talks about the reason we say possibility of organic life is because we can detect organic molecules in the atmosphere.
So I think on the video that I watched, it said that for the atmosphere, they look for the hydrogen helium component. And if they don't find that, that means it's more of a rocky planet.
Okay.
And so that means it has more of a possibility of having like organic matter or like water.
Very good. I don't know if what you heard, what Nicole said.
That was the video link that you
The one we
shared.
showed?
Yeah.
Oh, okay. Well, what y'all saw, I didn't catch that. But if the atmosphere is minus hydrogen and helium, it's got other things, then
Yeah.
that
Means like it's less of a gaseous planet.
Yeah, excellent. Very good. Okay, well, that's all I have today. So this will start in lecturing on the sun on Monday.